check this out. We did a problem last class where we looked at equilibrium situations. Right? We had this nice problem. We had a positive, +4 positive charge, and a negative charge, and we tried to figure out, where you have to put that charge for an equilibrium. On your homework, if you've looked at that yet, there is a similar problem there where, let me bring that up here. Let's see, where's that problem? It's number 5 on the last homework. It's basically the same thing. And what we found, which was an interesting result, was it doesn't matter if there is a positive test charge place or a negative test charge place. Didn't matter which charge it was, there was never going to be a situation where the charge would move. And that's sort of fascinating because it sort of reveals that the test charge is unimportant. There's something inherent about what we call the source charges that really determine what happens. And so this has sort of developed into what we today call the field model. With the field model, and field models popped up in all sorts of areas of physics, and it's when you get to higher level of physics, it becomes a more and more important idea because there's a lot of mathematics behind it. But the idea with the field is that the source charges create an alteration around them, and that when you apply other charges to the alteration, they respond to it. So you don't actually need the source charge there, or the test charge there at all. It's something that is inherently around. And you can kind of see it here in this picture with magnetic activity. You can see these iron fillings form patterns. Okay? And so if we take these magnets here, right, put them in contact, these patterns form. If I were to take another object, like today I take a compass needle, and I place it down next to them, it's going to experience an interaction. But we can visualize how that looks by the iron fillings here. So this is a nice visualization of what that field might look like. The idea that you have sources and test charges, and that the alteration of space, is due to the source charges there. You don't really need to have, those test charges in there. So we have this object here. A produces the field. B responds to the field. Now, one of the reasons why this is nice is because a lot of times we're looking at interactions. And the interactions actually don't really require us to know what it comes from. We don't have to know that. All we have to do is know how it should behave in the presence of the field. And so that's why we're going to develop this idea, because it's very powerful. And it's going to be connected to ideas of energy later in the class, which, energy is always a pretty nice thing. So here is our definition of what our field is. So if you imagine so if we have, these 2 point charges, okay, if we have a force that we can talk about that acts on them, and we divide that by Q, where Q is our test charge, okay, so we can apply a charge. If you divide out one of the Q's, what you will get is you'll get an expression for the electric field. So it has a very similar appearance to Coulomb's law, except it has one less Q in it. And the Q that is in there is what we call the charge. It's the one that's producing the field, and other things are going to respond to that field. Okay, now the units of this are exactly what you might expect, newtons per coulomb. That is not the only unit that we will have for electric field. Later in the class, when we develop energy ideas, we will introduce a slightly different unit. Okay. Also note that this is a vector quantity. Okay. And that vector quantity will always be aligned with the force vector. Okay. So for example here, if, we have an electric field here, and if the force points to the right, the electric field will also point to the right. Question for you already. An electron is placed at the position marked by the dot. The force on the electron is what direction? Which direction is the force? I got 60 people in here. Wow. So many bees. But it's A. The answer is A. No, what's going on here? Well, the idea is the direction of the force. Let's go back. Let's go back. We're going back. Why? Exactly. So the definition here is it's the force vector divided by the charge, the test charge here. Now, if the force vector, now we see the electric field points to the right. Now here, now remember what negatives do. Negatives serve one purpose. And negatives serve to indicate the correct direction. You will notice that in this definition here, there's no absolute value on that Q, like we had in Coulomb's law, because the sign does matter because it will flip the direction of the electric field. Okay, so the force is actually to the left in that picture there, and it's because if the force vector points to the left and the charge is negative, the two negatives cancel out and the electric field points to the right, it's positive. Okay, now the general rule is this, however. Positive charges will flow in the direction of the electric field and negative charges will do the opposite. Okay, it all comes from the fact that positive charges are sort of our convention for this. All right, and negative charges will do the opposite. Okay, well, it does. Moving on. Right along. Okay, well, that looks like an electron there, right? No, it doesn't. Okay. Good excuse, though. Good excuse. All right, what is the correct electric field direction at the dot? So we have a negative charge here. It produces an electric field. And then the dot is this thing here. Now that's a real dot, not an electron. This is not even an electron. This is some negative charge. It could be an electron, though. And what's the correct electric field direction? A lot of B's. Little N mixed in there. All right. Answer is B. Why? Well, the electric field, another way to visualize or to understand the direction of the electric field is, what would a positive charge do if placed in the field? If you put a positive charge down at the dot, the electric field, okay, well, the positive charge will experience an attractive force that will take it towards the negative charge. So therefore, the electric field points in that direction. Okay. So again, there's a couple ways to think about this. If you have an electric field, positive charges will move along the field and negative charges move against it. And then when we have a situation like this, we're dealing with the source, we want to figure out what the electric field is. The convention is, what would a positive charge do? What would a positive charge do? So that's the idea. And of course, you're going to be doing this a lot on the homework. This is an idea that needs to stick in your head here. Okay, but the convention is, the default convention is positive charge. Okay. Let's keep chugging along here. All right, so if you are presented with an electric field, we can rearrange that definition and we can determine what sort of force is going to be exerted on a charge that is placed in that field. Okay, so this Q here is what we call the test charge, not the source. You put it in the presence of the electric field, and there is a force that is simply a scalar multiple of the electric field. But again, this Q in here can be positive or negative, and the purpose of any negative sign, or positive sign for that matter, is to indicate the direction. So if you have an electron, the force is going to be opposite the electric field. If you have a proton, the force is along the direction of the electric field. Okay, same deal, just saying it in a lot of different ways. All right, so we can take the simplest example we've developed so far, and that is the point charge. And so here we have our source charge, which we'll call Q, and we have a point that is at some distance from there. And if we were to put a test charge here, which we'll call Q prime, it would experience the force that you see here. Therefore, the electric field is in that direction at that particular location. It has a now it's Coulomb's law here, but we divide out the Q prime, and we're left with the electric field being very similar to Coulomb's law, except there's only one Q at the top, and it's that source Q. And this is a vector statement, and we still have this sort of vague way to express direction. In this case, it's away from Q. If there was a negative in here, it would be toward Q. But that's what the electric field's going to be. But this is only for a point charge. Only for a point charge. We're going to develop, really what we're going to be doing over the next several weeks is figuring out what the electric field is in a variety of situations, not just point charges. Those are simple. We want to do the more complicated stuff. That's the idea. So let's talk about this. What is the direction of the electric field in the regions shown below? Okay, so this should be very familiar. We've pretty much already done this already. But the idea here is, if you were to put a test charge down, what would it do? So let's talk about that. Let's draw some arrows here. So if I put it, now I'm looking at part A here. If I put a test charge down on the left-hand side, okay, and that charge is always going to go to the left because of repulsion. Same thing here. On the right-hand side, everything is going to be pulled away here. When it comes to in between, you got a tug of war going on, right? And so there's pulling going on either sides, and that means there's got to be an equilibrium position here. At some point, you can get, now obviously if you're in the middle, right, what's going to win? The positive 4 charge is going to win. But we got to move a little bit closer. We got to skew a little bit over to the single positive charge to, figure out, what's where the equilibrium is. And the equilibrium is actually right here. And it's that same principle we talked about in the other class. Look at the distance. The charge ratio is 4 to 1, right? So the distance ratio needs to be 2 to 1. So there's 2 units of distance from positive 4 charge and 1 unit of distance from the 1 charge there. If you think about the ratio, Q over R squared, okay, you got a Q over R squared for the single one here, and on the other side, you have a 4Q over 2R squared. So you square the 2, the 4's drop out, and then you see that you actually have the same expression there. Now, of course, if you're inside here, though, you're going to be, oh, that's not what I want. The direction of the arrows, it's all about repulsion here. Why can't I get rid of that? I don't know what the heck's going on here. All right. So I'll just draw arrows over it because I can't seem to get rid of it. It won't select it. Stupid zoom. All right. So everything kind of points into the middle there. And so, all right, yeah, that's your equilibrium. Now, the problem down here, we did this one last time. And I'm going to stick down the equilibrium right now. Right here. Again, you got 4Q here, you got 1Q here, but the tug of war is not taking place in the middle. The tug of war is taking place out over here. This is 6 units from 4Q and 3 units from the negative charge. There's our equilibrium. And let me throw down some arrows here. If you're over here, a positive charge is being pulled away. If you're in here, everything goes towards a negative charge. If you're here, things are going towards negative charge. And then when you get far enough away, the 4q becomes the dominant charge there. And so those would be the directions for the electric fields, which, by the way, this picture, at least at the bottom, because we did this problem at the bottom here, that picture is the same picture, right? Because the electric field and the force vector are always going to be aligned, because we're talking about positive test charges here. Now let me just check out the homework, because I think in the homework, excuse me, no, what about this homework? No, I don't know. I thought I had that first problem up there in the homework, but I guess I don't. Maybe I did at one point. I don't know. Maybe I did. I kind of do, kind of don't. I just don't, actually. All right, let's move along. Let's move along. Let's do some numbers here. What is the strength and direction of the electric field 1 millimeter from a proton? What is the strength and direction of the electric field 1 millimeter from an electron? Okay, let's do it. Let me bring up my something here. Something. I don't know where. Is this it? No, that's my slides. This is hard. All right, where did I put this stuff? Put it in. Not there. Not there. Not there. There. All right, here we are. The electric field of a point charge. You know what it is. KQ over R squared. And it's a vector quantity. We haven't really talked yet about how we are handling this vector yet. I'm going to keep you in suspense for a little while more. It's away, right? Positive charge, electric field points away. So it's going to be 9 times 10 to the 9 for K. Q is 1.6 times 10 to the minus 19. If it's a proton or electron, fundamental charge. Otherwise, you'll be given the charge. Okay? Distance down here, hashtag I use meters, 0.001.
We can't see
millimeters down there. Don't you dare. That's
frozen. We can't see anything, Professor.
Yeah, we're looking at your files right now.
Oh, you kidding me? You kidding me?
Yeah, we can see it now.
If screen share was a person. All right. What are the strengths? This is, I know it's my fault. I mean, I'm the dumb one here, clearly. But still, I got to blame somebody else, obviously. All right. So, who is this? Who owns Zoom? CEO Zoom. You're going to get a nasty little note from me. Eric. All right, Eric. Not his fault, too, either, I guess. Someone needs to be the fall guy. All right, anyway. KQ over R squared. You heard what I said before. 0.001 on the bottom here. And we get a electric field. One of those days, everyone, it's not just one of those days. It's every day. Every day, bro, with that coronavirus flow. That's how it is these days, right? Anyway, 1.4 times 10 to the minus 3 newtons per coulomb away. Okay, now maybe I'm talking about this today. I don't even remember now. But R hat, it's a unit vector, and it means directly away. It means radial. Okay, radial direction, which is our way of saying directly away. R hat is tricky. It's tricky. Okay. So, but the interpretation, it means radially away. The reason why it's tricky is because there's I hats and J hats going around, and they're different compared to the R hats. So we'll work on the R hat. I think I am actually going to get into it today, though. Okay. Let's do it. What about the electron? Guess what? Not different. KQ over R squared Well, the fact that it's an electron, again, this is your test charge. We don't care about the test charge from electric fields. So the magnitude is exactly the same. However, the direction is different because the electron's negative. It's going to flip the direction of that. And so you get 1.4 times 10 to the minus 3, but now it is toward. Okay, toward. All right. So, and these are vague terms anyway, but yeah. All right, let's move on. Let's see if I can not screw up the screen share this time. That would be nice. That would be lovely. My mouse is now invisible. That's cool. Whatever. All right. What is the strength and direction of an electric field that will balance the weight of a 1 gram plastic sphere that's been charged to -3 nanocoulombs? Okay. Ooh, this is a good one. Ooh, this is so good. I should actually have a question that precedes this, because there's some tricky stuff here. Let's do it. Free body diagram of plastic sphere. Gravity goes down, therefore the electric field must point upward, right? So that's clear in your free body diagram. The electric field must point upward. Sorry, no. The electric force points upward, right? If gravity is down. But look at the equation here. The electric force is equal to Q times the electric field vector. We have a negative charge. So the field needs to be down. Because if your field is down, now we don't know where this field comes from, and we don't care. It's just there's a field in this area, and it points downward. And if you stick a negative charge in that field, it will experience a force that is upward. Okay, again, it's due to the nature of the scalar multiplication here for your vector quantities. So, but the way you would, the best way to visualize that is to say, okay, well, I know gravity's down, and I know that the electric force has to be up, negative charge, therefore electric field needs to be down. We equate the two forces to each other. Mg equals QE, solve for E, capital E, mg over Q, okay? Kilograms, got to do kilograms, okay? 9.8, 3.0 times 10 to the minus 9. That's the nanocoulomb thing. Then you got 3.3 times 10 to the 6 newtons per coulomb. Now that seems big, because it is big. You may ask yourselves, like, well, look, why don't we do this? Why don't we just have things floating all over the place, and let's just crank this electric field up, and let's just make certain things float. Okay, well, guess what? We're talking about a 1 gram plastic sphere. That is tiny, and we can levitate it, but 3.3 times 10 to the 6. The electrical breakdown of air, I believe, is 300,000. No, it's 3 million, actually. So this is a tad above. I thought it was 300,000. It's 3 million, though. 3 million. So this is a tad above the electrical breakdown of air. Therefore, if you want to do this, the air surrounding the plastic bead will turn into a plasma. And that's a cool prank, but you'll kill people in the process of that. So yeah, electrical breakdown is not, you don't want that. So these electric fields are too big. So this is not a practical thing to do. All right, anyway. Let's get back to the slides here. Okay, so now we want to try to visualize what's happening here, okay? And there are a couple ways that we can visualize our electric fields. And that's done in a couple different ways. One is called a field diagram, and one is called electric field line diagrams. They're slightly different. This is just a general field diagram. And what it is, it has points that are not exactly evenly spaced, but they're just, they're in the vicinity of our charge. And every point indicates what the electric field would be like at that location. And so you can see here, points that are close in have very large lines. As you get further away, the lines get shorter. And the idea here is that you could, interpolate what's going on in any other part, right? I mean, if this vector here is really long and that one's a little bit shorter, and there's a little bit of a distance here, if I put a point down right here, you're going to have a pretty good sense of what direction that is. It's radially away, and you'll get a sense of how long that vector is. It'd be somewhere in between the two that I pointed out here. So it's a nice way to sort of depict, how the field's going to look when you look around the point charge. Okay, I think I have a negative one next. Oh, no, I don't. Oh, here's the R hat stuff. Cool. All right. So, now that we're showing the field diagrams, now we care a lot more about direction now. So now I'm going to formally introduce the unit vector R hat. Okay, unit vector R hat, and that has a meaning which is, by definition, a little vague. Okay, so you're in context here. You always have to, put it in terms of, what those symbols are. So the idea here is I have, a location here, right? And I want to indicate the direction toward different points here. So say there's a charge here, and I'm trying to indicate, the direction of the electric field at points 1, 2, and 3. And the way I do that is I have to visualize this this R hat vector. Okay, and a lot of times I refer to it as the radial direction vector. And it's very simple. It just always points from this charge to the location where the electric field is being evaluated. Okay. Now, in some cases, it's very easy to figure this out. Like over here, if you look at electric field 3, R hat is actually negative I hat. Simple, right? If you look at like number 1, though, it's a little more complicated. If you there's a lot of situations where, yeah, you can express things as R hat, but if you're going to have to start solving problems, eventually you do have to break things into I and J's. And so this vector here has an I component and a J component. And so R hat here can be written in terms of I hats and J hats, as long as the vector magnitude still equals 1, because that's what you need for unit vectors. Okay, we're going to do a couple examples today, so you'll see how that is done. Okay. All right, so here is our electrons field diagram. And so what we could do is we could state now what the electric field is in terms of our new R hat vector. It has a nice little form now. Okay, you interpret this R hat to mean radial direction. If it's positive charges, they're radially outward. Negative charges are radially inward. Okay, great. You're doing on time. Fantastic on the time. All right, question for you. Put it in the chat. At which point is the electric field stronger? I'm going to let you think about this tough one here. You are interpolating, right? Filling in the blanks is what interpolation means. Fill in the blanks. Read between the lines. That's a good one. Kind of apt, right? So yeah, if you're closer in like that, you can see these lines. Now, the actual electric field vector would be shorter than this one down here, but it'd be longer than this one over here. It'd be pretty close, I guess, in length there. Find the strength and direction of the electric field at the dots. Everything's good here. All these are good problems. Good problems. Fun. All right, so now here is the most tricky thing about this is the R hat. All right, that's the most tricky thing about it. Now, we got a positive source charge here. So I'm going to draw in with an arrow, what the electric field's going to look like. Now, I'm going to try to do this relatively speaking. So this one over here is going to point away. Not quite as long. Let's make it a little shorter because we're a little farther away, right? then this one here is even farther away, so I'm going to make that one even shorter. But that's the direction of those electric field vector lines, okay? And what I decided to do is I added an additional point down here to go over in a little more detail how we're doing the Rhat stuff. So I don't... What is making that noise? Oh. There's a point down here, and I didn't really specify a distance there, but so I'm not gonna really indicate a length per se, but it's it's something like that, right? Or actually, you should put the vector there. So I don't really know how long that is. Let's just make it like that or something like that. All right, so let's think about our Rhats. You look at this and say, what's the direction? Well, it's just up. So Rhat is Jhat. That's it. So you replace the Rhat with the Jhat. Number 3, that's easy. Rhat is Ihat. Very simple. Now, for anything in between, or anything that's not orthogonal, like vector number 2 here, it goes up at an angle, right? So I can specify what that angle is. You can see from the geometry here that whatever angle is present right here is the same as what's right here, right? Those are the same angles. And we can easily figure out what that angle is based on the sides. In fact, you don't really need to know the angle, and I recommend that you don't find the angle because you don't need it. So why get it if you don't need it? Because trig functions, and that's what these are, right? So here's what's going on here. Here's how we figure out what Rhat is. Rhat is going to be cosine Ihat. That's the component, okay? That would be the unit vector component, and then plus sine Jhat. That's the upward component there. And I can go ahead and put what those trig functions are. Remember, trig functions are at their core, they're ratios, right? So the hypotenuse here is clearly 5, so you have a 3, 4, 5 triangle. And the I direction is going to be 4 over 5, and the J direction is 3 over 5. And so there you go. That's my unit vector. That's my Rhat for this configuration here. And you can go ahead and verify this, but if you work out the magnitude of this vector, it has a magnitude of 1, which means it is a unit vector. That's the deal with the unit vectors. All right, now, down over here, I decided to create another point. It wasn't important for what we're doing here. I just made a point because I want to illustrate again how you would do the Rhat stuff. So here, the angle is defined with respect to a vertical axis, right? So then when I'm working on my components here, right, my opposite side goes with my cosine, right? And my adjacent side, well, sorry, no, the adjacent, no, what did I just say there? The adjacent side goes with cosine, but that's the y component. And the opposite side goes with sine, but that's the x component. Okay, now that x component is positive, so I'm going to get a sine, this is the Greek letter phi, doesn't look good, sine phi I hat. And then this component here is downward, so you'll put a negative cosine phi for your j hat. And that would be the unit vector at this location right here. Okay. And again, if you know the dimensions of the triangle and ratios, or just get the angle if you want to get the angle here. Now, that being said, I did somehow manage to grade your homework yesterday. I don't know why I did that. I just had the time somehow, and I just did it. And for the most part, it was okay, But and if you haven't done this yet, go back into the assignment. If you got anything wrong at all, I annotated stuff and I left little comments here, so you should look at that. Also, look at the solution that gets posted. Okay, but in there, one thing I emphasize is that when you have weird angles like this, you should always be using reference angles and then handling negative signs independently. Okay, because once you start throwing in cosines 210, a sine 135, it just gets more complicated. So a lot of times you double count negatives and things like that, and it just becomes a headache. And so I don't recommend you do it, and I think it's actually a better conceptual thing to always try to see the reference angles here, and then attach the appropriate sines and cosines and algebraic signs to them. Okay, so end rant. Now, for electric field number 1 here, it's kq over the distance. Use meters, right? And so whatever that is, I didn't work it out. Just plug in the numbers and you get it. 3 is similar, except there's a little bit different distance down there. And then 2, I actually had worked this one out. kq over the distance, which is 0.05 squared. And then I replaced all of r hat with what I worked out right here. And so now I have the components. The reason why, so we had a question about why the sines and cosines flipped here. That happens because we have an angle that's defined with respect to a vertical axis. And so, like, if you look at this vector right here, the one that we had for number 2, that vector, that angle is what we call standard position. So that means the x component is the adjacent side, it gets the cosine. The y component is the opposite side of that triangle, it gets the sine. Well, when you define things with respect to a vertical axis, everything gets flipped around. Now the y component, or the j hat stuff, is the adjacent side, so now it gets the cosine, and vice versa with the x component. Right? X component, opposite side, that gets the sine function on it. Yep. Okay, fantastic. Stop doing that, computer. All right. Anyway, so you punch your numbers in here. Hopefully I didn't screw this up. 28,800 I hat, 21,600 J hat newtons per coulomb. And I just worked it out for 2. Again, 4, the only reason 4 is here is just to illustrate what R hat is. I didn't, there's nothing to work out here. It's a great problem, people. It's a good problem. You should be, study this one. Study this one. In your homework, let me look for your homework here. I'm going to post later. What did I do with that? What's the date today? 26th? So you're going to be doing a bunch of R hat stuff here. And then at some point you get down here. Yeah, number 5. Number 5 is...
We can't see it. Yeah, we can't see it.
Oh my gosh. I clicked it though. You see that?
Yeah.
Okay.
Yeah, we see it.
I'm sorry. I gotta figure this out. I can't keep living my life like this. All right. Electrons place... wait. So number 5 is basically what we did here. You got at the origin, you got something going on there, and then at some other locations, you got to figure out it's the same problem, basically. But yeah, this is a fun homework. You're lucky. I give you the fun homework. Other teachers give you the boring ones. So, you're welcome. Oh yeah, this is a good one. It is a good one. All right, so this is a more complicated electric field problem to do. We have multiple charges involved. And superposition does apply here as well. Okay, so this is the original problem here, actually. Find the field created by the individual charges. Yes, you can see that. Thank goodness. You know what? I just realized how I can fix this problem. Quit my job. That's it. I just realized it. I just quit my job. No, actually, I'm going to sneak in here. Yeah, I'm going to have I have a computer on the left of me here. I'll just jump in as another student, and then I can just look over and see how dumb I'm being all the time. Okay, nice. Okay, so. All right. Yeah, that'd really screw you over if I just quit right now, huh? Oops, shouldn't do that. Anyway, all right. We are interested in what's happening right there. Now, can the principle of superposition be applied to find the net field? Well, the assumption is, well, force is a base superposition. Do fields obey superposition? Well, what's the relationship between force and a field? It's a scalar multiplication. And so is scalar multiplication, is that, well, there's a mathematical term for that. It's escaping me right now, but is that, is that map, or what's the term for that? I mean, basically, the scalar multiplication doesn't really change any of the physics here. Okay, forces have superposition, then fields do as well. There's a name for it, though. Is it, I can't remember. There's a mathematical name for that, like, like math proof name stuff. Can't remember it there off the top of my head. All right, so let's look at the solution to this. All right, so all these charges are the same. Thank goodness. This makes the problem a lot simpler. Right, now, I have drawn here, or the whatever figure I got this from, drew in the 3 electric field lines. Okay, and the top one here is going to go down to the right, up into the right, and then straight across. Now, there's a symmetry argument you can make here. Due to symmetry, the electric field of that goes up along the y-axis is going to match the electric field that goes down. So the j hat components of the electric field from 1 and 3 cancel each other out. And so what that means is your electric field is simply whatever the electric field from number 2 is, plus 2 times the x component of either one of those charges, because they are identical. I just said E1 here. It could be anything you want, really. I mean, it could be E1 or E3, I mean. So it's E2 plus 2 times the x component of, say, E1. So let's put those numbers in. The distance from Q2 over to point P is x, so it's KQ over x squared, I hat, plus, and now for the next one here, okay, we got 2 from the 2 up here, KQ. Now the distance is, you get it from the Pythagorean theorem here, right? How far are we from Q? Well, we have x defined, and then these charges are distance d above and below. So according to the Pythagorean theorem, that distance, the r distance from Q1 to P, is radical x squared plus d squared. But we're squaring that, so it's just x squared plus d squared. Cosine I hat is the r hat part of this, at least for the x component. Okay, so if you take the adjacent side of the angle here, that's the x component, so it needs a cosine here. Now we can work out what that cosine is, because you don't want to leave this as cosine. Okay, because here's the thing. There are currently effectively 2 variables here, x and theta. But theta has x built into it, so you never really want to keep the cosine like this. I mean, this problem doesn't have numbers in it, which I love. But if it has numbers, we'll just throw numbers in there, fine. But if it does have numbers, you have to write, your trig functions in terms of the spatial variables here. So the cosine, which is given right here, is going to be the adjacent side, which is x, over the hypotenuse, which is radical x squared plus d squared. So when you combine that all together, you get a 3/2 exponent up here. And so this is your expression for the electric field. Let's try to clean this up a bit. If we clean this up a bit, then what happens is we take the KQ out, and we get a 1 over x squared plus a 2x over, and this garbage down here, I hat. Now, that's our electric field. But something kind of interesting is going to happen here, though, right? And this is something we're going to do a lot in our problems. Sometimes when you get an expression that looks complicated like this, you start to think about assumptions that can be made. You start to think about approximations, and you see if these approximations or these assumptions sort of hold, and that kind of tells you if the expression you have makes any sense. So here's what we're going to do. Let's imagine, right, that this point P is not very close, right, to these charges. I mean, if it is close to the charges, then this cosine factor is a pretty big deal. But if you're extremely far away, so say we put this point P, out to the moon, or something like that, crazy, right? What happens? Well, this d would be extraordinarily small with respect to x here. And so this sum, x squared plus d squared, is really just x squared. And then when you take the 3/2 power, you get an x cubed here. There's an x up top, there's an x cubed in the bottom, and you end up with a 2 over x squared. You can combine these together and simplify it to get an expression that would be 3 times kq over x squared, which would be the result if you had a 3q charge at the origin. But if you're so far away from the origin here, then that distance d becomes irrelevant practically, and it's no different than if you did have a 3q charge sitting down there. So that's nice. And that's, we'll do that occasionally, and sometimes we have to do that. In fact, we have to make simplifications like that to solve problems. You develop something more complicated, then you make an assumption or a simplification, and then you can actually get to a problem in a much easier way like that. So this was like a sanity check, right? Because the prediction is if we're super far away, this should just look like a 3q charge. And we did the math, and it does work out that way. So that's fantastic.